Okay, so this is a talk about what I've called the long and short of ocean tides. So hopefully what the long and the short are will become apparent as we go through. And that's what really makes this suitable for a conference on multiscale numerics, I believe. So we'll start off by looking at the long tide, which is what most people would think of as being the tide. So this is, we're looking here at sea surface height from -3 to +3 meters. And we're looking at an animation which is periodic with a period of just over 12 hours. And this is a data product which is taken from Oregon State. And it's animation of the principal lunar tide, which is the M2 tide. So you can see these amplitudes around the UK, say the tidal amplitude is going from maybe +1 or 2 meters to -1 or 2 meters twice a day. You'll notice the response here is generally pretty long, sort of basin scale in the open ocean, and even in the coastal seas, you can see the scale of the tides from space, let's say. Now, lower down in the ocean, there's something else going on, which is the short tide, which is the internal tide, and the idea is that the barotropic tide, the surface tide, is being forced astronomically. So there's a deep horizontal flow associated with that, approximately depth independent. And where that deep horizontal flow encounters submarine topography, for example, this chain of seamounts here, there is some vertical flow necessarily induced at the sea floor. The interior of the ocean is stratified. The vertical motion, periodic vertical motion, excites internal waves. And internal waves are generated near the topography and propagate away into the deep ocean, away from the topography. And this is a little simple animation of the M2 internal tide.
What's the amplitude?
Well, can I answer that later, Alan?
Yes.
You got in quickly. This is simulation. This is a very simple model simulation for illustrative purposes only. And the key point to take from this is that this internal tide has to have some energy. It's, as the waves propagate away, they take energy, and they're taking it from the surface tide, the barotropic tide. Okay, so in doing that, they exert a drag on the surface tide. So if you want to model the surface tide, you also have to model these guys, because these guys exert a drag on this system. So it's a completely coupled system. So what I'm going to talk about is producing numerical models of this tidal system. We're certainly going to need astronomical forcing in, ocean bathymetry, stratification, but the class of models I'm interested in are those which do not use any observations of present-day tides. So they're purely dynamical, predictive models. And there's three aspects to them that you have to address. First of all is what are the physics, what are the important physical processes which have to go into such a model. Second issue is really mathematical. What's the most convenient way to write down the equations of motion? Free surface flow over large topography for a stratified fluid. And then the third issue, of course, is just solving these equations efficiently. And it may be a good point just to think about why we might want to do this, because if you actually want to know what the tides are in the present-day ocean, the best thing is just to look at a long time series at the point of interest, and then you can see what the tide is. This sort of dynamical model won't do any better than data. So you might think that this is the kind of problem we should be able to solve. If we know all the physics, surely we should be able to get a good numerical solution. So that's part of the motivation. Maybe we don't know all the physics. Maybe there's something we've missed out. Another issue is that if you have such a model, then you can use it to think about what the tides may have been in the past or the future. And there's quite a lot of interest in what tides do in terms of, well, at least in terms of the internal tides, what they do in terms of mixing in the deep ocean, for example. And there's quite a lot of interest also in paleotides in the deep past and how they may have interacted with ice sheets and other climate forcings. So I really want to be able to do all this fairly efficiently so that we can make lots of runs for different scenarios in the past and the future. So the outline of the talk is as follows. I'll start off with physical background because otherwise you won't know the requirements for the numerical model. And then in part 2, I'll just quickly review the standard strategies for this sort of modeling, varying degrees of complexity. And then I'll tell you about the alternative approach which I take, which just takes two assumptions or two approaches, neither of which is particularly earth-shaking on its own, but they're not used in this combination for global tide models at the moment. And I'll tell you why I think this leads to a more efficient solution method. I'll then look at how you can apply this to model the surface tide, which is all based on inversion of large matrices. Then I'll talk about a second problem, which is, given a surface tide, how can you model the internal tide using this approach? And then at the end, I'll wrap these two things up together to tell you about a complete tidal model. Okay, so there's quite a lot. I'm going to cover quite a lot of ground, but in a fairly light way, hopefully. So physical background then, of course, everything starts with the sun and the moon, which I hope you recognize. The sun, of course, is much bigger than the moon, but the moon is much closer to the Earth than the sun. And for tides, the relevant combination is mass divided by distance cubed, and it happens that the moon wins over the sun by a factor of 2 in terms of tidal forcing. These are the accelerations that the astronomical bodies cause in the ocean, which are very tiny, 10 to the minus 7 meters per second squared. But of course, if you integrate that over a tidal period, which is 6 hours, a quarter of a day, that's 20,000 seconds, then that implies velocities of about, well, if you multiply that by 20,000, you get 0.01 meters per second. So you're expecting velocities of about a centimeter per second in the deep ocean from this tidal forcing. And in shallow seas, you'd expect the velocity to be much higher. Typically, h depth times velocity would be approximately constant. You might have speeds of 0.1 or 0.2 centimeters per second in shallow seas. And each of these will excite a tide, slightly different periods. Situation's a little bit more complex. I mean, if the Earth's rotation axis were in this plane, and if the moon was also rotating in the same plane, and if all the orbits were exactly circular, you would just have those two tides of period 12 hours and 12.42 hours, but that's not the case. Everything's inclined or not perfectly aligned, so the resulting tidal potential has a whole range of frequencies, but they're all clustered. Well, the largest ones are clustered around semi-diurnal and diurnal. And of course, you can work out what these frequencies should be. Well, or Victorian mathematicians could work out what these frequencies should be from very long calculations. And each of these frequencies has a letter and a number ascribed to it. This is a George Darwin notation. So M2 is the principal lunar tide twice a day. S2 is the principal solar tide twice a day. And here are some diurnal tides, K1 and O1, with these particular frequencies. And if you take any tidal signal, this is just 2 weeks of data from Liverpool, the home of British oceanography, or British coastal oceanography anyway. If you take any tidal signal, you can decompose it into a sum of these constituents. And around the UK, the largest constituents are always semi-diurnal, but in other parts of the world, the largest constituents can be diurnal. So today, you'll hear quite a lot about M2 and K1. And you can look at those constituents also from space. These are, again, the products which are derived from Oregon State, which are a combination of dynamics and data. It's a data assimilation problem. And these are views of the amplitudes of these constituents in meters. So here's M2, up to 3 meters, very large in the North Atlantic, which is why we in Britain are very keen on this one. S2, similar frequency, similar pattern, smaller amplitude. And here are the diurnal maps. Almost nothing in the North Atlantic, but there's a lot of action in the Pacific in both of these maps. And this is by far the most energetic, M2. 312 petajoules, that's the kinetic and potential energy summed together. So as I said, I'll be focusing on these two guys mostly today. Okay, so I mean, the basic dynamics is pretty clear. You've got the astronomical forcing, which is approximately independent of depth over the ocean. So you can think about sort of two big flaps just going down into the ocean and pushing the ocean backwards and forwards. Sea surface moves up and down, and that's what we see. But there's quite a lot of other dynamics going on, which of course you need in a tidal model. The first piece of which is called the self-attraction and loading term. So this is an incredibly unlikely term to appear in the dynamics, and it arises as follows. This is a simplified picture of the Earth and ocean, not to scale. And these perturbations here are supposed to represent tidal perturbations. And there's a mass perturbation, positive, negative, associated with this. And you can work out the gravitational field associated with those mass perturbations in a standard way. Del squared of the potential is equal to the density change. So idealizing the density change as a delta function at the surface of the ocean, this would be the equation to solve, where zeta is the sea surface height perturbation. It's a gravitational field, surely tiny. Well, it is very tiny, but also the gravitational or the tidal accelerations we've already seen are 10 to the minus 7 meters per second squared. And it turns out if you take the gradient of this potential, it is of the same order, 10 to the minus 7 meters per second squared. You can solve the problem mathematically using spherical harmonics. That's the solution, which you can find in Lamb's book. We're just interested in the bit near the surface. And I mean, this is kind of interesting for all sorts of theoretical reasons. Numerically, it's important because if you want to calculate this potential, you have to do something akin to taking a spherical harmonic transform, doing some operations in that space, and then doing the inverse transform back to physical space. Okay? There's also an extra effect that the Earth deforms under the extra weight of even a meter of water, which you have to take account of, which is the same order of magnitude as this term. Right, what else is going on? Well, we've talked so far about there being a deep flow, independent of height, that the Sun and Moon excite. Of course, near the bottom of the sea, right at the sea floor, there can't be any horizontal flow because there's a no-slip boundary condition. So there's some sort of boundary layer, which is typically a turbulent boundary layer, quite thin in the open ocean, possibly several meters in the shallow seas. And in terms of the depth average dynamics, you can think of this as inducing a stress at the sea floor, turbulent stress. G.I. Taylor was the first to really explore this in great depth, and he noted that if you that there's observational evidence and scaling arguments suggesting that the drag would scale like this, like velocity squared. And the question really is how significant is this dynamically? And it turns out to be rather significant, and you can see that through a very simple calculation, taking a typical velocity on the shelf seas. You can estimate the magnitude of this stress, and then you can estimate how much energy this sort of bottom drag is taking out of the tide over the whole globe. So that's just force times velocity times the total shelf area, and you get a figure of 1 terawatt. Okay, so that says that, well, if you believe this, then 1 terawatt or 10 to 12 joules every second are going into this bottom turbulence. And that's significant because if you take the energy of the tide, which for M2 is 300 petajoules, divide it by this dissipation rate, you get a damping timescale of a few days, okay, which is not a lot longer than the tidal period. Okay, which suggests to me that this friction is actually dynamically significant. So that's process 2. So we've had self-attraction and loading, bottom drag. And then process 3 is this internal tide generation, which we've already seen from top. Here's a view from the side. So this is a simple 2D model with a slope. So this is height and horizontal. And we're looking at cold, dense water and warm, light water. And we're looking at a tidal flow just going from right to left to right. So it's pushing the water up and down the slope. And the internal waves being generated, propagating off to the left and to the right. You'll notice that, I mean, this is just a simulation at a particular set of parameters, but you'll notice that you get these interesting beam-like structures coming off the topography, which is quite typical for when the slope is steep. These beams can actually be highly turbulent. There can be very strong secondary instabilities or convective overturnings in them, which won't concern us today. These internal tides have a small surface signature, only a few centimeters, but the perturbations in the ocean can be 100 meters or more. These can be truly massive waves. But they're also fairly short wavelength at tidal frequencies. Okay, I mean, compared to the sea surface, which has a very strong restoring mechanism going up and down and is a very fast wave, the internal waves, it's a relatively weak restoring mechanism, which leads to a relatively short wave speed. So at tidal frequencies, you get a short wavelength. And these things really are observed in nature. Here's some observations from Hawaii. This is just 24 hours of time, so 2 semi-diurnal tidal cycles. This is a little bit of the ocean from 1150 to 1450 meters in depth. And we're looking at temperature. So this is just a proxy for vertical motion on these time scales. So you can see, if we say follow the yellow, you can see the water going from 1100 meters all the way down to 1450 meters and back up. Okay, so 150 meter waves inside the ocean. Okay, so that's the physics of the tidal system. We have directly forced barotropic or surface tides, which in turn force bottom boundary layer turbulence and internal tides. So there's energy going in these directions. So accompanying that, there's a drag on the barotropic tide. Barotropic tide itself, of course, is a steady state phenomenon. So this has to be taking energy from these guys up here, and it's well known that the energy shows up in things like lunar recession, for example. So we know that there's 2.44 terawatts coming from the moon to here, and that 2.44 terawatts has to be going out into these routes. Okay. Right. Okay, so how are we going to numerically model that? Well, there's some fairly obvious things we're going to have to put in, like astronomical forcing, bathymetry, ocean stratification, something about the elasticity of the Earth, because the Earth is compressing under the tides. And then this is a list of desirable features your model may wish to have. I mean, of course, it's got to have free surface dynamics, which are basically shallow water dynamics, because these waves are very long, which means very high wave speeds, about 200 meters per second in the deep ocean. Your model needs to be global. Okay, you could probably remember from the animation, you could see the tides propagating from ocean basin to ocean basin. You can't just model the Atlantic and get the right answer for the Atlantic. It has to be linked to the other basins. Experience shows that if your model's much more than a quarter of a degree, you won't get the dynamics right. So we're certainly going to need, let's just say, roughly a quarter of a degree grid size. If this is your wave speed, that means your time step's going to have to be rather small. Particularly if you've got converging meridians, you might need a time step of 20 seconds at this kind of resolution. You're going to have to account for the turbulent bottom boundary layer. And there's no known, well, I'm not an expert on ocean models, so I don't think there's any ocean models that have a turbulent bottom boundary layer resolved globally. So this is always parameterized in ocean models. In tidal models, in tidal models, typically using the standard formulation. You need self-attraction and loading, which typically is implemented using a spherical harmonic transform. You can also do it with a convolution integral, but either way, there's some sort of global integral to be solved. Internal wave generation, you need to have in. The wavelengths of that are rather small, maybe 10 to 100 kilometer wavelength. So your grid size is probably, if you want to see this, it's going to have to be maybe 10 kilometers or less, just roughly. You might also want to get those internal wave beams in, maybe. So that's really the wish list. Apart from this guy, you can get away surprisingly well with just looking at linear solutions. Okay? So in the open ocean, the tide is clearly linear, the surface tide. It's very long wavelength, very small amplitude. In marginal seas, certainly there are non-linear overtides, but the dominant dynamics is still linear. And even the internal tide generation itself, at heart, is a linear process. It's just water moving up and down a slope. Now, the generation and development of that tide is definitely non-linear. Okay, but the actual magnitude of the generation, in quite a few studies, has been shown to be well approximated, and that's a key word, approximated by linear dynamics. So if you're interested in modeling the magnitude of the internal tide drag, you can get away with linear models. Okay. But of course, it doesn't tell you things about where the internal tide energy goes to, which is of great interest to many people, but not for me today. And of course, efficiency is desirable because you may want to run this for a whole range of paleo scenarios, maybe. Okay, so the simplest thing you can do, and this has, it has a history going back beyond these papers here, but these are the more recent, what I'd call the modern versions of this approach, is simply to say, we'll throw away the internal stratification, we'll throw away the internal tides, and we'll parameterize the internal tide drag. And then you're in single layer shallow water land, and you just start from rest, put the forcing in, time step the equations, wait for the things to settle down, which takes about 20 days usually, and then you then time step and do a spectral analysis of your signal. Okay? And according to how many constituents you have, you may need to time step for a long time because the frequencies of the constituents are all clustered around 12 or 24 hours. Some of them are very close together, and you may need to run your model for about 200 days to separate some of these components. So these papers are all at this sort of resolution, 1/2 to a 1/12 of a degree. There's a parameterized internal tide drag in here, and usually there's some unknown number in there which can be tuned to make your solutions look good if you wish. Problems with this are, well, the self-attraction and loading is always done approximately because none of these models calculates a spherical harmonic transform at every time step. Okay? In fact, a lot of them don't even bother calculating spherical harmonic transforms at all. They just use various approximate versions of self-attraction and loading. So that's approximate. And of course, the internal tide drag is the big problem with these sorts of things. It's a parameterization. And a parameterization of bottom drag is one thing because that's a sort of a local process, and you can see or feel why the amount of drag might be very strongly linked to the velocity at a particular location. Internal tide drag, it's a process which is to do with the shape of the slope. So it's non-local. It involves, you can't just parameterize it locally because the extent of the wave generation depends on the width of the slope, the height of the slope, which you can't express at a single point. It's also got non-trivial dependence upon all these parameters, and it also depends on frequency. And of course, it's hard to parameterize something that depends on frequency in a time-stepping model, where you have no knowledge about frequency. I don't wish to be too hard on these models. You can see my name up here as well, so somewhere. They do a very good job. Okay? So the next step up are the multi-layer shallow water models. So you include some stratification in a simple way. So here are 3 papers which use this approach, and here's a very nice picture from the paper from Simmons et al. From 2004 showing the interface displacement, and I think this was a 2-layer run, this one, and you can see these internal tides being generated at various hotspots like Hawaii and Tahiti and propagating very long distances across the ocean. I should say that Bob's hiding in the et als in 2 of these papers, I believe. These models are much better. You don't have to parameterize the internal tide drag, and you get explicit modeling of the internal tides, albeit in a simple way, particularly if you're at this end of the number of layers. There's still issues with spherical harmonic transforms and the like. So that's level 2. Level 3 then is to go to a full ocean circulation model, which is becoming more common. So there have been 2 recent papers published which are using large models at high resolution. And all they're doing, of course, is putting in the tidal forcing, which often isn't included in such models. Running them for a long time, doing the spectral analysis. So again, now you have explicit modeling of the internal tides. You can include things like interaction with the general circulation and eddies if you think that's important to the physics. And again, there's no spherical harmonic transforms because it just makes it too expensive. So this is the kind of result you get out from these models. So this is a figure from Brian Arbick's paper showing sea surface perturbation in red and some altimetry data in blue. And this is the sea surface perturbation due to the internal tide. So this is a test of how good your internal tide dynamics are in such a model. So this is along a particular track of satellite data, probably in the Pacific, I would imagine, going to 40 degrees north. You can see this very weak surface signature of a few centimeters, and you'd probably say that agreement is not bad. I mean, it's the right kind of amplitude, it's got the right kind of wavelengths in. I mean, some places it looks better than others. But it's important not to be okay, I'll rephrase that. These resolutions, I mean, even though they're quite high, they're not really that high for internal wave dynamics. So if you're running a model at a 12th of a degree, you probably want, I don't know, maybe 8 grid points across the wavelength of your internal waves, maybe. So that means you can probably see internal waves with a wavelength of a bit less than a degree, so maybe 60, 70 kilometers, something like that. And what is the wavelength of the internal waves? Well, this is a plot of internal wavelength versus ocean depth. So this is wavelength in kilometers versus ocean depth. And I'm looking here at the first 4 internal wave modes within the ocean at M2 frequency. So if your model can see things with a resolution of about 2/3 of a degree, which is up here, this dashed grey line, it means you're seeing quite a lot of the first internal wave mode in the off the shelves, plus a little bit of the second internal mode in the deep ocean, but not a lot else. So even though you've got 40 layers in height, you're only really seeing 1 or 2 internal wave modes themselves. Well, this is a, so I've calculated these from a stratification, sort of a mid-Pacific stratification, and omega, so I'm just calculating the long wave speed without rotation in it. Yeah, I guess so, yeah. That's another way to put it. Okay, so that's the state of affairs, and of course those models, I mean those are the state-of-the-art tidal models. Okay. So I'm doing something a bit different, which is as follows. So the first thing is I'm taking linear dynamics for the reasons I've already explained. I'm taking, so these are linear Boussinesq equations, hydrostatic. Here's the density equation. It's Boussinesq, so here's an incompressibility condition. All the forcing and nonlinear drag and self-attraction is just hiding in this term for the moment. I've got no normal flow at the seafloor, and then I've got continuous pressure and the kinematic condition at the free surface. So that's what I'm solving for the rest of the talk. And this is the first key approximation, that if you're interested in internal wave dynamics, the thing you should be, your mathematical formulation should go after the internal waves. Okay? And the way to go after the internal waves is to look for solutions which have just the right vertical structure. So if you take a simple scenario here where there's constant depth and no rotation, you can look for these simple traveling wave modes, speed c, and some unknown vertical structure z. Substituted into here, you get an eigenvalue problem for the vertical structure. So c is the eigenvalue, the wave speed, here are the boundary conditions. And out of this comes a single barotropic mode, that's the surface mode, the shallow water mode as it were, and then the internal wave modes. So that's just the calculation which leads to this sort of picture here. Now, each of these modes is in essence an internal wave. Okay? So what you can do is you can expand your solution. So here I've taken horizontal flow and pressure and expanded in terms of these eigenmodes. Okay? This is a Sturm-Liouville eigenvalue problem, so you know this will converge in the mean at the very least. You can substitute these into here. Well, actually, sorry, you can multiply these equations by the eigenfunction, integrate, and see what you get. And you're going to turn this into a problem for the modal expansion coefficients. Okay. And what comes out of the following, so I've distinguished here between the barotropic mode, which has got a subscript 0, and the internal waves, which have a subscript greater than 0. And if we look at the top equations first, the stuff in black is just linear shallow water equations. Nothing else could come out of this than that, with P0 being g times the surface height. Except there's a term in here to do with the internal waves, which is the internal wave drag. And it's just the baroclinic pressure multiplied by the gradient of the topography, which is what it should be. And then you also get an equation for the internal waves, so that's the red stuff. And in that equation, there's a term due to the barotropic forcing, which says where the deep tide hits topography and hits it, so u dot grad h is non-zero, you get waves, internal waves generated. And the nice thing about this formulation is that everything's gone into there, the top boundary conditions, the bottom boundary condition above an arbitrarily shaped seafloor. So you've removed the geometry from the problem completely. All these coefficients depend on depth, and depth, of course, depends upon the two horizontal directions. Okay, and you can calculate all these coefficients. And to my knowledge, this was first done in this paper, although not very elegantly. So this is the model that I'm going to use. Of course, you might be concerned about this sum to infinity over here, which is, I mean, that's the price you pay. So you have to truncate that, of course. So it has to be a sum over finitely many modes. And the kind of dynamics that come out of this model are these kind of things. So here are these simple solutions, again, in 2D of internal wave generation. And this is what internal wave generation looks like with just 2 vertical modes for 16 or 32. So these are that's the movie I showed you before. So you can see as you include more modes, you get more detail in your solution, of course, and you start to see these beams coming out. But even with a few modes, you can already start to see where the beams are. And in fact, most of the energy in these sorts of modal decompositions is in the low order modes, provided you're looking at topography which is sufficiently wide anyway. So later on I'll be showing you solutions which have 4 internal wave modes in them. Okay, so that's part 1 of the alternative approach, is to use a modal decomposition. So 3 spatial dimensions plus time becomes 2 spatial dimensions plus time with coupling between a few of these modes. Okay. Then the second approximation is, well, if we're looking at linear equations and if the forcing is at known frequencies, then the response is also at known frequencies. You can just look for solutions at those specified frequencies, and then you get rid of time as well. So then you'll have something like this. So then your 2D plus time, well, the time's going to disappear into this. So you then get 2D PDEs on the sphere, which are elliptic in nature, with some coupling between a few of these modes. So what's going to happen is that instead of doing time stepping, you're just going to have to do direct inversions of equations, probably with some iteration. So you're really trading long runs with memory-intensive inversions. Although you might have to worry about things like nonlinearity, nonlinear drag, and things like spherical harmonic transforms, which I'll come to. So for the next, I'll just go through these 3 bits. I'm going to use this approach in the following way. First of all, I'll just look at barotropic tide solutions without worrying about the internal tides. That's sort of the heart of this system. Then I'll look at internal tides using this formulation with a prescribed barotropic tide. And then I'll look at the problem where these 2 things are coupled together. So these will just be about 6 or 7 minutes each, I think. So for the barotropic tide then, we're just looking at the 0th mode of our modal decomposition. I'm going to expand that as a sum of tides of particular frequencies. So there'll be capital J constituents here. You can choose that. And then the shallow water equations become this, with forcing, self-attraction and loading, and bottom drag, or drag, which could be nonlinear bottom drag or internal tide drag parameterized. So, I mean, once you've done a discretization, everything over here is linear and sparse. so probably invertible. The forcing, that's going to stay on the right-hand side. This term is linear in basically sea surface height, but it's dense. Okay, it's a spherical harmonic transform and operations plus inversion. And then there's some nonlinear bottom drag, which you can project back onto the. So here this is a solution of frequency omega j. So you can work out the projection of the nonlinear bottom drag back onto there. Okay. So the way to solve this then is to just write your solution, I guess, as a big column of all your unknowns. Then the system becomes just linear dynamics with forcing, self-attraction, which is dense operation, and nonlinear friction, which is nonlinear on the right-hand side. And the way you can solve this is iteratively. I mean, the subtlety being that you can't just keep these guys over on the right-hand side. They're just two big terms. You need to have some essence of these two terms over on the left-hand side. So you have to construct sparse approximants to these terms, which you can drag over to the left-hand side of the system, and then you're hopefully left with small residuals over on the right-hand side, and then you just iterate this system round and round and hope it converges, which it does if you do the right averaging after each time step. So the dynamics here, or the way you solve this problem, is to make this thing as easily invertible as possible. So I use the simplest possible numerics. So this is, I feel quite embarrassed talking about these numerics at a conference like this, but this is how things are. So this is a regular C-grid rotated pole, second order finite differences. You can do a higher order finite differences if you want, and just put the extra terms over on the right-hand side. So at 1/4 of a degree resolution, there's about 700,000 grid points. So this matrix over here is about 2 million by 2 million with about 10 million entries. And you can just iterate away. And typically, this thing converges for me in about 10 iterations. Here's a plot of maximum difference between iterations as a function of iteration number for a solution with 8 different tides in. Get this very nice, robust scaling in the iterations. And each of these solves, the way I do it, on a desktop machine would take about a minute, maybe. So it might take 10 minutes to do each of these constituents, and then sort of order of an hour for this whole thing to work. And I'll just show you some solutions to show what they look like. Here is M2 model, and here's M2 data, as it were. This is tidal amplitude, and this is tidal phase. And the agreement's pretty good. That's not a big deal because there's parameterized internal tide drag in here. And you can make your model look, well, not almost perfect, but if you're willing to tune the drag, you can make it look very good. So I don't wish to say this is a great solution. Even this one, it's a little bit too energetic around here. But you can clearly see that this gets the basic dynamics right. Okay, so that's the first problem, the global barotropic problem. The second problem is the internal waves. So we're now looking at these guys down here. So the second problem I'm just going to look at for the moment is, let's suppose we know the barotropic tide, what internal waves do we get? So we're going to be solving these equations here. And you might say, well, why don't I just repeat the trick that I just did? Write all the linear dynamics as a large matrix. I've got some forcing and just do some inversions. Well, the problem, of course, is that the internal wave length is much smaller than the barotropic wavelength. Okay, so you just can't do that. Well, you can't do it. So somebody can probably do it. I can't do it globally. But the good news is you don't have to do it globally. If you're just interested in the size of the drag, all you really need to know about is what's going on at the generation site. Okay, the waves are going to be generated. They're going to go off and do something, which is interesting to many people, but not to me today. So all you really need to do is look at locally. You need to just look at these equations locally, and then you'll be able to back out what this internal tide drag is and probably feed it back into a barotropic model. So I'm going to do local modeling. I divide the ocean up into 112 is the magic number boxes, which are chosen to coincide with features like Hawaii, or the Aleutian Islands sort of align with topographic features. And on each of these I will solve the internal wave problem. So the problem just reduces to this, internal wave dynamics plus forcing. The solutions I'm showing you today, I'm neglecting the coupling between the internal wave modes. You can do iterative solutions to account for that, but I'm not going to show you those today. And for each of these domains, you can calculate, you take a buoyancy frequency, so you can calculate all the internal wave speeds from an eigenvalue problem, discretize, and then the waves are going to radiate out through sponge layers. And for these solutions, each of these is discretized at about 800 by 800, and there's 100 boxes like that. So what does it look like? Well, this is a sort of typical solution. So here's a Nova Scotia solution. So Alan, are you still awake, Alan?
Yeah, I'm listening.
Here's your scale you're asking about. This is bottom pressure due to the internal waves. It's newtons per meter squared. Okay. So this is a model domain. Grey is land. The light grey is regions where the waves are damped. So these are sponge regions, so you can see the waves are going into the sponge regions and not reflecting out. There's also regions near the coast where the waves are damped because the wavelength of the waves is just too short in shallow water to see them. So rather than generate junk, I'll just damp out. In fact, I don't actually force any internal waves in these regions because there's no point. The model can't see them. So in this simulation, you can see there's a lot of tide generation at the shelf break, as you'd expect. Big internal tides propagating off into the deep ocean, small internal tides propagating onto the shelves in a somewhat unrealistic way. And if you look at that mode by mode, this is what the solution looks like. There's 4 vertical wave modes. This again is newtons per meter squared bottom pressure, and the scales are different for each of these modes. The largest response is almost always in mode 1. So you can see as you go from mode 1 to mode 2 to mode 3 to mode 4, the wavelength gets shorter, as you'd expect. And then for mode 4, I'm not really resolving an awful lot of what's going on. Okay, it's just too short wavelength. You can see some interesting things, though. For instance, at these seamounts over here, you can see them exciting mode 4 internal waves, which are then propagating away. Here's some stuff at Hawaii. So here's the island chain of Hawaii. Here's M2, and here's K1. So these are different internal tides, different frequencies. So this one's got about twice the wavelength of this guy. And if you work out how much energy is coming out from the prescribed tide, up here it's 19 gigawatts, which is in line with estimates, observational estimates. In K1 it's a lot smaller. Aleutian Islands. This is what you have. Same sort of classic picture for the M2 tide. Just classic radiating internal waves. For K1, you can't have radiating internal waves at those frequencies because the forcing frequency is less than the Coriolis parameter. But you can get trapped waves which will propagate along the topography, and they seem to be strongly excited in this model. Okay, so that all looks very pretty. Is it at all relevant to reality? Well, that's a hard question to answer because what reality is for internal waves is poorly constrained. Okay, because you can see them on the surface, so there's a bit of an inverse problem as to work out what's going on down below. I mean, of course, there are lots of very good local observations of internal tide generation, but there's no global picture. So I'll just show you what there is in terms of global modeling. The way you can try and work out how much energy is going into these internal tides globally is you can take a shallow water model, a single layer shallow water model, and just put an unknown drag on the right hand side, constrain that model with observed data, and then try and find the drag that best fits the dynamics and the data. So you can sort of deduce where the drag is, and this is what Egbert and Ray did in a series of classic papers in the early 2000s. And then you can sort of divide up your domain and put drag in different boxes. So on the Hawaiian box, for instance, they find 18 gigawatts of internal tide generation. So here are some of their different boxes, and here are some of my different boxes. This is a very rough comparison. Rough in the sense that the boxes are different boxes, but they're in roughly the same place, and also rough in the sense that this is only an estimate. Okay. So with all that in mind, the agreement is encouraging, I would say. I would expect these figures, in principle, to be less than these figures, because the model doesn't have all the internal tides in it, just has a few. It's got 4 vertical modes, which should be the bulk, but it's not going to be all of the energy. And that's particularly, seems to be the case, the mid-Atlantic, which is known to be a very rough area of topography. This estimate is quite low. Okay, so very rough topography, you'd expect a lot more higher order internal waves to be generated. And if you look at the global picture, this is what it all looks like. So this is stitching together all those 112 boxes and looking at the dissipation. And the total dissipation in this model due to internal tides is about 0.6 terawatts. And we don't know what it is in the real ocean. Some people think it's about 0.8. I personally think it's likely to be quite a bit bigger than that, probably about 1.2. So if you believe my belief that the total conversion should be 1.2, then the model I've just shown you is getting about half of it. But I could be wrong. I probably am wrong. Okay, so just to summarize that then, I've shown you 2 things: barotropic tides, which are modeled using what I'm calling quasi-linear shallow water equations. They're linear apart from bottom drag, which is non-linear. Seeking solutions at fixed frequencies. You can then find multi-constituent solutions using sparse matrix inversion with iteration to account for non-linear drag and the dense self-attraction and loading. And at least in my experience, this is much faster than the traditional shallow water approaches. So it takes about 10 minutes per constituent. And on a desktop, if you do the time stepping, or at least if I do the time stepping, it takes about 10 hours per constituent. I've also shown you an internal tide model, which is based upon a modal decomposition. And the point of that is it targets the internal waves. You just have 1 degree of freedom, and it gives you the full vertical structure of the internal waves. Okay, so you don't need multiple layers to resolve an internal wave. Again, if you work in the frequency domain, then you get down to sparse matrix systems to be solved. I've shown you these solutions in 100 patches because it's a local generation problem. They were solved at a 40th degree. I don't think I mentioned that, sorry. So that's quite a bit higher than the global models are running at. And we certainly see wave generation, which is roughly consistent with observational estimates, but I can't say any more than that. So then this is the big picture, that we've solved this problem, which is, well, not solved. We've got a solution to this problem, calculating the surface tide globally. With that surface tide, you can then force the internal tide model. Once you force the internal tide model, you can work out where the drag is, and you can then feed the drag back into the next iteration of this model, okay, which is already an iterative solution. So it's no real big problem. So this is a kind of like a low resolution global model, and these are very high resolution local models. And it works sometimes at the moment. So here's a single constituent solution. This is a convergence plot of difference between iterations as a function of iteration. So you can do a lot of these barotropic iterations, just take a few minutes each, a couple of minutes each. When you think you've got a reasonable tide, you can then start firing away these internal tide models. Even on a desktop machine, just doing this in serial, each of these would take about, well, in this one they took about 5 hours each. So this whole model is sort of like a 2-day simulation. Obviously, if you do it in parallel, it will be sort of a 15-minute calculation. And I could show you results from this, but they won't look any different to the results I showed you before, because, as I said, I'm only getting, even at this relatively high resolution, I'm only getting probably half of the internal tide drag, or thereabouts. So if you're willing to take a parameterized internal tide drag and tune it, you'll still get better solutions. But I'd argue this is probably a physically more sensible thing to do. Okay then, so just to finish, tide models need to account for a range of things: astronomical forcing, realistic bathymetry, bottom drag, internal tide generation, and these gravitational self-attraction and loading effects. Most modern tidal models that I know of are based on time stepping, and they're computationally expensive. I mean, of course, that's fine. I mean, if you've got a big computer and you're willing to run it for a long time, that's fine. But even the ones, well, certainly the ones which are published, are still barely resolving the internal tide generation and have approximations to this term, which is a little bit concerning. I think working in the frequency domain is much faster and more elegant, really. It means you can also implement this term exactly. And then I'm claiming that if you couple this with low-order internal tide models using the modal decomposition, which goes straight after the internal tides, then you can get a global model which you can run at fairly high resolution, even on a desktop machine in a reasonable amount of time. So that's what I've shown you today. Of course, there's a lot more to be done here, and this is being done by Vladimir, who's a postdoc in Leeds, who's sitting in the middle of the room. So this is his list of things to do. Of course, you really need to include more internal wave modes to see more of the internal tide dissipation, coupling between the modes, weak nonlinearity in the equations, which you can account for by building them into the iterations. I'm using pretty simple elliptic solves for all of this, so Vladimir is looking at better implementations of these. He's also going to do a parallel implementation of the internal tide model, which will really make this an extremely fast model. And of course, I mean, ideally you also have variable resolution. I mean, I think all the global models I know of, apart from one, are just standard or fairly standard rectangular grid models. There's a French model, French finite element model, which has higher resolution over the shelves and the deep ocean and the ridges in the deep ocean, which is what you really need. So that's another thing on the list for Vladimir to do. Okay, thank you.
Your implementation of the self-attraction term, you're doing that with spherical harmonics. Could you also just solve a PDAE using kind of grid-based method to do that?
Non-local, right?
Yeah, he's asking if I can write del squared phi, or maybe not del squared, operator of potential equals something on the sphere and solve it. I'm not aware of a formulation like that.
I have been asking everybody who seems like a good mathematician I've found for the last 6 or 7 years, and nobody can tell me how to do that. In 3D, right? So Stephen showed a lovely little innocuous-looking equation. 3D del squared phi equals something on the right-hand side. There's a source term, which looks really innocuous, and you can rewrite that in 3D in an integral form. Well, you can also write that in terms of an integral form in 2D. The thing that I don't know how to do, and I can't find anybody who will tell me how to do it, maybe because it can't be done, is how to write that as a 2D del squared just on the surface of the sphere. If you had that, then everything would just kind of lay itself out beautifully for the sort of approach that you're asking for. But unfortunately, when you apply a delta function of mass at the surface, you're wanting to do a double integral over a delta function. And so in the vertical, to collapse it down to 2D. And that's where it gets, well, beyond my level of mathematical abilities.
I'm sorry to drop you in it, Bob, but I knew he knew the answer better than I did.
Okay, so right. Okay, so this equation is in 3 dimensions.
Yeah. And this is a solution in 3 dimensions.
For some reason, the projection, the shallow water version of that is not.
It's still 3D.
It's still 3D.
Yeah. Okay. The solution is still 3D, of course, and then you take the bit at the surface of the
So the answer is yes, if I have a 3D grid instead of a 2D grid. Okay.
Yeah, that would be one.
Right.
So one of the things that you're using is the annual mean stratification, which may be fine in the deep ocean, but near the surface, that's probably not such a good approximation, and that may in fact change the vertical modal structure. Have you thought about kind of playing around with different season stratification as a way to see whether there should be a seasonal signal in the internal tides?
I've thought about it, and it's certainly on the list of things to do. But there's, I mean, I guess I would think that there's probably higher order things still to be fixed with this to make it a bit better. I mean, certainly you could start using it to look at science questions like that, but I haven't done that. And of course, that's one advantage. I mean, as you know, of course, the time settling models, which are run over multiple seasons, the ocean circulation models can see all that without any extra trouble. But of course, I could, as you're suggesting, just do a spring run and a summer run, and that's not too much of a trouble because it's fairly fast.
So the map of dissipation you showed was incredibly inhomogeneous. It's
Yep.
sort of localized in.
Yeah, it's all over the topography.
Of course, dissipation is related to internal mixing, which is very important for driving the ocean circulation.
Mm-hmm.
So has anyone thought of taking that a field like the output tree or model and feeding that into to drive an ocean GCM?
Yeah, there are some people who do that. That simultaneously they will have tides in a model, and they'll calculate the dissipation as they go along, and then they'll change the vertical mixing according to what the energy transfer is. So, I mean, for instance, Green at Bangor has a paper on that for paleo tide application. But there are other people have made some calculations like that as well.
The big challenge here is the high modes don't get very far before they die, observationally. And so for those high modes, the high vertical modes, actually they don't even necessarily become modal. They don't necessarily propagate as far as the surface. You take a map like this and you put in energy and you say, okay, what's the vertical buoyancy flux that energy can support? And that gives you mixing. The much more challenging one is the low modes, exactly the ones that Stephen is describing, because this tells you where they're generated. It doesn't tell you where they go to die. And the mixing occurs wherever they die. So there's a beautiful example off of the Campbell Plateau, just south of New Zealand, where you have this incredibly intense generation site. You can see it kind of hanging down. Well, the mixing from that generation site, these things get beamed across towards Tasmania. And so most of the mixing doesn't happen near New Zealand, it happens near Tasmania. And I mean, this is oceanographically really convenient because there's an oceanographic center in Hobart, and so you just sail offshore and measure them, and you're measuring the mixing effects of what happened in New Zealand. But how to put in that non-local aspect, which is just critical, because you care about where the mixing happens, not where the internal waves are generated. That's a big deal, and there are a number of us working very hard to figure out how to grapple with that.
Yeah, the papers I've seen where they do calculate dissipation and then calculate mixing, it's just all done locally. So it doesn't have that kind of importance as.
But it's only half the energy. I mean, Stephen's getting half the energy to go beaming across ocean basins. So it says that there's a big gap.
Thanks, Stephen, once again.